Good morning, students. Welcome to the mass transfer course. Today will be lecture 16. Here we are discussing about the interphase mass transfer, and in last day we have determined the overall mass transfer coefficient, that is Ky, which is based on gas phase driving force. What is the driving force? YAB minus YAB star. And what is YAB star? What is the XAB, that liquid bulk concentration? If I take that equilibrium value of this, that is the YAB star. And for that one, that what relation we got? 1 by capital Ky, where Ky is the overall mass transfer coefficient, equal to 1 by small ky plus m dashed by kx. Similarly, if we consider the overall driving force from the liquid phase point of view, so that time the driving force will be YAB star minus YAB. What is YAB star? That is the equilibrium value of YAB. Okay. So this is the driving force, and corresponding overall mass transfer coefficient is capital Kx. Capital Kx equal to 1 by Kx equal to 1 by m double dash small ky plus 1 by Kx. And here m dash and n dash are the slope of the equilibrium line at different point. But if this equilibrium line follows the Henry law, y equal to mx, so that time that m dash equal to m double dash, this will be the m. And here we told, although we have taken the example of gas liquid, but this interphase mass transfer will be applicable for any two phases. If I take liquid, gas solid, whatever phase we will take, same principles will be applied. Okay. So instead of gas liquid, we can tell it G phase and L phase, where G phase and L phase can be any two phases. Today we will solve three problems to get better understanding of these overall mass transfer coefficients. So first thing is about the Henry law, and we told that Henry law is applicable for dilute solution cases. It is not necessary to be that ideal gas phase or liquid phase should be ideal, but when in dilute solution concentration of solute is low, then it has seen that is linear, and that is the Henry law, y equal to mx. But Henry law can be expressed in different way, and you should know, if let's check, if I have a PAXA, okay, the partial pressure in gas phase, and this is the mole fraction. So if it is expressed in this way, Henry law, but if I need to solve the problem, if I need ya equal to mx, then how will we convert this thing, or some other form, or it can be that PA equal to some constant into C. So different possibilities are there in terms of Henry law. That let's see how it can be done. The solubility of a gaseous substance A, okay, the molecular weight is 26. The gaseous substance molecular weight is 26 in water is given by Henry law, that is Pa equal to 10 to the power 5 into x, where Pa is the partial pressure of A and Xa is the mole fraction of A in the liquid phase, and this is the Henry constant m. And what is Pa? It is expressed in millimeter H, millimeter mercury. convert the equilibrium relation to the following forms. So this form you have to convert YA, that is mole fraction of A in gas phase, equal to M into XA. This is the mole fraction in liquid by M. What will be the value of M if the total pressure is 10 bar? B is PA, that will be same, but in terms of XA, that then it is CA, that what will be its that Henry constant, where CA is gram mole per liter. Okay. And equilibrium relation using mole ratio, assume that solution is a dilute and has a density equal to that of water. So solution is dilute and density of the water is 1000 kg per meter. So I have that Henry law is given in this form PA, but you have to express this in this form or this form. Then what will be the value of Henry constant? Because it is required according to your problem, you need to convert this in different forms. Okay, so how will you do this? So let's see the first one, A. So total pressure is, what is this? Y equal to mxa if total pressure is 10 bar. If 10 bar is the pressure plan, then what will be its Henry M. Now we know 1 atmosphere equal to 1.01325 bar. So total pressure equal to 10 bar. 10 bar equal to 10 by 1.013, that is the atmosphere, into 760 millimeter of mercury, because it is expressed in terms of millimeter of mercury. So I have to convert this in terms of millimeter. So that is 7520. Okay. So equilibrium relation, what is given? PA, what is that unit? Millimeter mercury equal to 10 to the power 5 into XA. Okay. XA. So YA, now I have to express in YA into XA. So Y equal to PA by P. So PA equal to 10 to the, okay, this equal to 10 to the power 5 by this into X. So if I PA equal to this, so I am dividing this PA by P, then this part also I will divide by this P. Okay. So what is P? This is the 750. So now if you take this is equal to 13.3. So YA equal to 13.3 X. Okay. So this is my relation in terms of YA, mole fraction of A in gas phase, and mole fraction of A in liquid phase. That is that Henry constant. Henry constant is 13.3. And it was given in this form. Now I got convert this in this form. Now if you take this M equal to 13.3, then you tell me whether it will be highly soluble or less soluble. So if 13.3 means M is much greater than 1. So in this case, concentration of gas phase will be high and concentration of liquid phase will be low at equilibrium. That's mean it is a less soluble solid. Okay. And if M is less than, let's say if it would be the 0.1, then it would be the highly soluble. So see, still now you have seen okay, Henry constant value is this. Up to that you understand. You don't bother what is its value. Now you have to think about its value. If value is high means less soluble, value is low means highly soluble. Okay. Now second thing I have to do what? Pa equal to m dash in this form where Ca is gram per liter. Okay. So Pa I need not to change. Pa is same. So I need to Xa to Ca, that conversion is required. So what is Xa? Xa is equal to Ca concentration mole solute per liter by Ca mole solute per liter plus Cw mole solute of water per liter. Okay. Now if it is a dilute solution, so whatever the concentration of the water, it will almost this, you can neglect this term, this part. So Ca mole per mole solute per liter, and concentration of water is 1000 is density by 18, that is gram mole per liter, or mole per liter. So if you take this one, so this will come Xa equal to Ca by 55. But if it would not be the dilute solution, if it be given the 13%, 14%, accordingly you can do it. Okay. So this is the relation. Now I will put in this equation Xa equal to Ca by, so Pa into 10 to the power 5 Xa I will put Ca by this. Okay. So Pa equal to 1800 C. So in this case m dash equal to 1800 millimeter mercury gram mole per liter. Isn't it? And in this case m is unitless. This is mole fraction unitless, so it will be, but in this case that m dash will be, that unit will be millimeter Hg gram mole per liter. Okay. So I can convert that same, all are Henry's equation, but in different forms. So first one is given, second one mole fraction, both are loss fraction. This is concentration, this is Pa, partial pressure. Okay. Now let's see the third one. Third one, what was this? This is equilibrium relation is in mole ratio. Mole ratio means Ya, capital Ya, X. Assume. Okay. So we got this small Ya equal to 13.33 Xa. We got this from first solving problem. Now we have to convert it in terms of capital Y. We know that small Ya equal to capital Ya plus 1 by capital Y. Okay. Because you know that capital Y equal to Xa by 1 minus Y equal to Ya by 1 minus Y. So if you convert this equation will come, or from this equation it can become, you can convert this also like this. So Ya, small y equal capital Ya plus 1 plus Ya. So 1, if you minus 1, okay, so 1 minus Ya, this, then minus Ya, this will cancel out, and if you take the reciprocal, capital Ya equal to small Ya by 1 minus small y. Similarly, if you take this one plus sign here, okay, then it will convert to here. Okay. So capital Ya and small ya, the relation, either you can put this or you can put this. Similarly, I can put Xa equal to X by 1 capital Xa by 1 plus capital Xa. So Y, small Ya, I will put this one, I will put this one, and 13.3 small Xa, I will put this one, I put this one. Then I will take minus 1 both side. So if I take both side, 1 plus Ya minus Ya by Y, and this is 1 plus X minus 13.33 X by 13.3. So 1 by capital Ya equal to 1 minus 12.33 Xa by 13.33 Xa. So if I take the reciprocal, so Ya equal to 13.33 Xa by 1 minus 12.33 Xa. Okay. So this is the relation of Henry's law in terms of capital Y and capital X. So why it is required? Because in the problem statement the Henry's equation will be given, one form will be given, it may be any form, but according to your problem statement you have to convert it. So you should know this, how to do this, because always we will see whenever we will solve this problem, always we need to draw the equilibrium curve. Without equilibrium curve, first thing we have to draw the equilibrium, because equilibrium curve will tell you how much, up to what point extent you can do the mass transfer. Because when you will reach to the equilibrium, then net flux will be zero, no mass transfer will take place. Okay. So this is the first problem. The second problem, at a particular section of an equipment for absorption of the solute A in a liquid, the bulk gas phase contains 9.5 mole percent A and liquid contain 2 mole percent. So gas phase and liquid phase, two phases are in contact. Solute A in the gas phase is 9.5 mole percent, and in the liquid contain 2 mole percent of it. The gas filling coefficient is 10 kilomole per hour meter square delta Y. Okay, so you can understand this. And 60% of the mass transfer resistance occurs in the liquid film. So here one mass transfer coefficient is given, that is gas phase mass transfer coefficient, and they are telling that 60% of the mass transfer resistance occurs in the liquid. The Henry's law applies Ya equal to 0.85 x. So you have to calculate overall mass transfer coefficient capital Kx, molar flux of A, and the interfacial concentration of the solid. Keep it in mind, interfacial concentration you cannot determine experimental, but you can calculate. You can determine the concentration of bulk phase. Yes. You can experimentally determine the bulk phase concentration of gas phase, that YAB, and bulk phase concentration of liquid phase YXA. That you but interfacial concentration experimentally not possible. You have to calculate from theoretically, and we know how to calculate this one. So that thing we will do it. So bulk concentration in the gas phase YB equal to 9.5% equal to 0.095, liquid concentration XP equal to 0.02. The total resistance in gas phase on gas phase basis 1 by capital OI, okay, equal to 1 by K small ky plus M Kx. Here M is the Henry. The 60% of the this is the total resistance. 60% of the total resistance lies in the liquid phase. So this is the total resistance, and 60% of this is coming from the liquid phase. What is liquid phase resistance? This is equal to this M by Kx. Now I know 0.6, Ky equal to 10, M equal to that 0.85, Henry is constant, Kx equal to 0.85 by Kx. Now Kx equal to 5.67 kilopole per meter square is delta X. Okay, and that small ky was 10 kilomole per meter square at delta Y. Now overall mass transfer coefficient capital Kx, I can capital 1 by capital Kx equal to 1 by small kx plus 1 by mky, because you see that m double dash, now it is as it follows the Henry law, so that slope will be similar because it is a straight line. Okay. Now Kx equal to 1.56 plus 1.85 by 10, and this resulted the Kx equal to 3.41 kilomole per meter square. Okay. Now we have to calculate the flux. Okay. So how will we calculate the flux? I will calculate the flux Na equal to capital Kx is known to me. Okay, capital X. So xb is known to me. Okay, that is 0.0. What is the concentration in the bulk concentration in the liquid, and this will be the bulk equilibrium bulk concentration. That is means whatever the gas phase concentration Y, corresponding that equilibrium value will be it, isn't it? Because if you see, in this case, this YB star, this minus this, so this will be the whatever the bulk concentration gas phase, that equilibrium value will be there. Okay, this is the driving force, because I am now determining based on the Kx is known to me now. Okay, so this, because Kx I know, this is just I calculated 3.41. Okay, now xb is 0.05. now what will be xb star? Xb star will be, we know that YAB, that is 0.095 by 85. It is would be in, what is the equilibrium value of this gas phase concentration? That is 0.112. Okay, so this, that's that thing I'm putting directly, this by this. Okay, YB by x star, x star equal to this by this. Okay, so this value, and then the flux you can calculate, that is 0.313 kilomole per meter square. Now how will you calculate the concentration? Because I know this, I know the flux. Okay, I know Ky, small q at 10, Yb is 0.095 minus Yi. I will calculate this way. So Yi equal to this. So if Y, then Xi will be, because Yi Xi will be in equilibrium, or Xi will be Yi by m equal to this point. This. Okay, so that I did for the from the, and so Xi equal to 0.075, Yi equal to 0.0637. Okay. I have calculated based on the gas phase. You can calculate the liquid also, because you know the, then it will be Na will be small k x xi minus xb, because you know the small kx, so you can calculate, because you know the moles kx, accordingly that way also calculate. Anyway you can calculate this, it is not a problem. So here we have calculated the overall mass transfer coefficient, flux and intermediate concentrations for the given problem. Third problem, it is the controlling resistance in mass transfer. What is the thing? Jasmine is a high value product used in perfume and cosmetic industry. So jasmine is one component which is used for in perfume industry and cosmetic industry. A suspension of jasmine flower, how jasmine will come? It generally comes from jasmine flower. So if you scratch the jasmine flower in liquid, okay, with water, then jasmine will come out. So then a suspension of jasmine flower in water is, now you have to extract this jasmine. Then how will you extract? So jasmine is in, after crushing the jasmine flower, it is in water phase. Now I have to bring this jasmine from water phase I have to separate this from water. So how will you separate? So I use one organic phase, so that jasmine will come from water phase to organic phase. So that is the concept. Okay, so a suspension of jasmine flour in water is contacted with an organic solvent to recover the compound. During extraction, the compound diffuses from aqueous phase to dispersed organic phase. The individual mass transfer coefficients are 3.5 into 10 to the power 6 minus 6 meter per second organic phase and 2.5 into 10 to the power minus 5 meter per second in aqueous phase. The solute is 175 times more soluble in organic phase. That's mean if you see 175. Okay. And Y is the mole fraction of the solute in organic phase. Here Y is the mole fraction of solute in organic phase. The aqueous solution is dilute and total molar concentration of organic phase is 10 kcal per hour. Calculate the overall mass transfer coefficient capital Ky, which phase resistance control means which phase, if which phase has a more resistance means that phase is controlling this thing. Now if you see, X is the mole fraction of jasmine in aqueous phase and Y is in organic phase. Okay, so organic phase is Y I denoted and aqueous phase is this. Now what will be Ky? Ky equal to Kl organic. Okay, or that is given. If you see semi per second organic phase. So semi per second, and if you remember that will be the Kl, semi or meter per second, that is the Kl. Okay, if you see when you studied in chapter 3 that mass transfer coefficient, that when unit is meter per second or semi per second, that is Kl. Okay, now you have to convert in Ky. So how will this is the conversion factor. We have studied already this thing in chapter 3. That's why I am telling chapter 3 you have to remember how to convert one mass transfer coefficient into another. Okay, so now it is 3.5 into 10 to the power 6 rho by m organic. This is equal to 10. It is telling 10 kilomole per meter cube. So this is 3.5 into 10 to the power 5 kilomole per meter square second. Okay. Similar Kx, Kl aqueous into rho by aqueous, and it is nothing but water. Water is 1000 by 18 through 55.5, and this is the mass transfer coefficient Kl. So 1.5 into 10 to the power minus 3. Okay, so this is the molar concentration of 10 kilomole per meter cube, and molar aqueous is 1000 by 18, so 50. So now equilibrium relation is Y equal to 125. So Y is the concentration in organic phase, and this is the aqueous phase. Okay. So 1 by capital Ky equal to 1 by small ky plus mkx. Okay. So what is this? So 1 by 3.5 into 10 to the power minus 5 plus 175 m dash equal to this. So this is equal to total resistance. This is the resistance from organic phase, and this is the resistance from the liquid phase. So total resistance this plus this equal to 1,45,270. Okay. So 1 by Ky, 1 by this, that is your the overall mass transfer coefficient capital Ky, that is 6.88 into 10 to the power minus 6 kilomole per meter square second into delta Y. Okay. Now fractional resistance to the mass transfer offered by the organic phase. What is this total resistance and this, and organic is this by this. So So this by this equal to 0.2, so 20%. So aqueous phase resistance is 80%. So none of the resistance control individually, but contribution of aqueous phase is more. Okay. So if aqueous phase resistance is there high, so if I want to facilitate the flux from aqueous phase to organic phase, I should start the aqueous phase, not the organic phase, because maximum resistance is coming from the aqueous phase. Okay, so today we have solved 3 problems for better understanding the interface mass transfer, but mainly here we discuss in problem 1, that is how to convert the Henry's law in one form to another form. That is very important. Every time you need this one. Okay. Second and third, actually we have calculated overall mass transfer coefficient, flux, interfacial concentration and resistance, like this what we have discussed in our last 2 theory classes. Thank you for your attention. Have a nice time.